I think a couple of example problems are in order to help you pull together the information in the last video or two. So let's use rotational energy to solve a simple problem. We have a mass hanging from a rope, and that rope is wrapped around a big, heavy, drum-shaped, cylindrical-shaped pulley. So as M1 falls to the ground, the pulley starts to rotate and the string starts to unwind. So if M1 is released from rest, a height h above the floor, how fast is it going just before it makes contact with the floor? And here's some information: the mass of the pulley, the radius of the pulley, the mass of the hanging weight, and the height above the floor. And there's one more thing we have to know. We have to know what is the shape of this object that's rotating, because we're going to have rotational energy stored in that pulley. And so it's given here that it's a solid disk. So let's take a look at how we would solve this problem. This is a very typical energy problem. We want to say the initial mechanical energy and the final mechanical energy are equal. We can't say that if there are external forces acting on our system. So in this case there aren't any. We'll include the Earth in our system. There are no external forces. We also can't say that if there are non-conservative forces like friction and air resistance. But in this case there is no friction. We will ignore air resistance. So the mechanical energy will be the same at the beginning and the end of our problem. What kinds of energies do we know about? We know about kinetic energy. We know about gravitational potential energy. We know about spring potential energy. Those are the three we know about before our chapter on rotation. And now we can add in a rotational kinetic energy. We know about one more type of energy. So all of that at the beginning of our problem has to equal the sum of all the energies at the end of the problem. And this energy approach to solving problems, we will continue to use this even as our view of the world gets more realistic and more complex, and we are able to account for other types of energy. We'll just keep adding terms to account for different types of energy. But right now, this is it. So let's put in what we know. We have two objects here, but nothing is moving or rotating at the beginning. So there's no energies associated with those. There's no kinetic energy. There are no springs in my system. I can just cross those out. So initially, all the energy of the system is gravitational potential energy in M1. So this is going to be M1GH. And at the end, I've got M1 moving. It's now at its lowest point, so I'm going to call that zero gravitational potential energy. And I've got something rotating. So I have a 1/2 I for the pulley, omega squared. K rotational for my pulley. So we're given M1, G, and H. We know those. We're trying to find V final. So our problem is the omega and the I. What are we going to do with those? I, let's start with that. For a solid disk, rotating about its center point. We look it up in our textbook. Solid objects, you have to integrate over them to find I if you want to do it that way. Often you'll find in the textbook a table with all different shapes, disks, hoops, rods, spheres, hollow spheres, solid spheres, things like that. And the rotational inertia for a given axis of rotation. Because remember, if you move the axis of rotation, it changes the rotational inertia completely. I've found this in the textbook. I, for a solid disk rotating about its center point, is 1/2 the mass of the disk. In this case, we're calling it M pulley, times its radius squared, 1/2 mr squared. What we really want is the speed of M1. And M1 is moving the same speed as the rope. And the rope is located out here a distance r from the axis of rotation. The velocity of the rope on the rim of the pulley is equal to r times omega. So instead of using omega, I'm going to use v over r. And what v is it? It's the velocity of the rope, which is the same as the velocity of M1. So I'll rewrite the equation. I've substituted in for the moment of inertia. Sometimes you'll hear people call it rotational inertia, sometimes moment of inertia. I, 1/2 mr squared in this case. Omega was v over r, and now I can solve. So in this case, I get 4.1 meters per second. So this was a good example of how you would set up an energy conservation problem, including rotational energy. You have to substitute in for the rotational inertia. You'd often look that up in the table in the textbook. And you have to convert omega into a linear velocity. And we know that v equals r omega. And so what we really care about is the velocity at the rim of the pulley. That's where the rope is, the velocity of the rope, which is equal to the velocity of m1. And once we make those substitutions, then it's fairly straightforward to solve. Let's look at a problem with something rolling. Let's make it a solid sphere rolling down a hill. It has a mass m, a radius r, and it starts a height h above some level below, and we want to know how fast, if we release it from rest, how fast is it moving, translating, when it gets to the bottom of the hill, a height h below where it started. Energy initial, energy final. We want to say that the mechanical energy at the beginning of our problem and at the end are the same, and we can say that as long as we have no external forces acting on our system, and we can include gravity, we can include the Earth in our system, so we don't have any external forces. And as long as we don't lose any energy to friction, to non-conservative forces. So in this case, there is friction between the sphere and the surface. If there wasn't, the sphere would not roll down the hill, it would just slide down the hill. The friction causes it to roll. But when a solid, rigid object rolls on another rigid surface, we don't lose any mechanical energy. It will keep rolling forever. We don't lose any mechanical energy. In real life, objects aren't always perfectly rigid, and when things roll, we get what we call rolling friction. Let me talk about that over here. What happens as this object rolls, maybe the tires on your car, they bunch up a little bit right there. The material of your tire of your car is not perfectly rigid, it's soft, and as the tire rolls, it bunches up a little bit in front, and your car, that bunching up of the rubber causes friction within the rubber, heat it up. Your car actually is always driving over a little bump. So rolling friction costs you energy. In real life, when objects roll, there's a little bit of deformation happening, and we do lose mechanical energy. Something will not roll forever. But in our case, we're going to assume these are perfectly rigid surfaces, and so we don't have any rolling friction. So we don't have to worry about mechanical energy being lost to heat and other forms. All right, so our initial energy is all going to be gravitational potential, and at the end, the objects come down low enough where we have kinetic energy due to its translation, and we have kinetic energy due to its rotation. This is where I told you we were going to treat this object as if it was two separate objects, one that's moving without rotating and one that's rotating without moving. And that's what these two terms are for. The center of the sphere that's rolling down the hill is located a distance h above its final point, so mgh is its initial gravitational potential energy. If it was just moving at the end, 1/2 m v center of mass squared, and if it was just rotating, 1/2 I omega squared. So the two things we need here, I and omega. I we can look up in our textbook, solid sphere rotating about an axis through its center point. 2/5 mr squared, omega v center of mass equals r omega when something is rolling without slipping. So omega is v center of mass over r. What do we get? The square root of 10/7 times gh for the velocity of the center of mass. Turns out it's independent of mass of the object, which I guess makes sense. If you drop different objects, they all fall at the same rate. So rolling down the hill, the fact that the mass canceled out maybe is not so surprising. So those two examples should have helped putting some of the ideas from the previous videos together. Looking at an object falling and causing a pulley to rotate. In the past, pulleys were all massless, but now we have the ability to deal with pulleys that have mass, because as they rotate, they're going to have some energy stored in them. We can account for that. And in this case, an object rolling down a hill, we can account for that by saying an object that's rolling is equivalent to treating it as two separate objects, one that's rotating and one that's translating.